QuEra's Aquila is a 256-qubit neutral atom quantum computer, one of the largest publicly accessible quantum computers in the world. It consumes less than 7 kilowatts of electricity. The NVIDIA GB200 NVL72, the flagship AI training rack that Google, Microsoft, Amazon, and Meta are deploying in the data centers this channel has been covering for the past several scripts, draws between 120 and 132 kilowatts per rack. A single rack, 7 kilowatts versus 120 kilowatts, for a quantum computer that can complete certain calculations that the world's most powerful classical supercomputer could not finish in the remaining lifetime of the universe. IBM, Rigetti, Google, and D-Wave quantum computers draw approximately 10 to 25 kilowatts each. The power grid crisis that AI data centers are generating, the rising electricity bills, the nuclear power purchase agreements, the water crisis from cooling systems, the 10% of New York State's peak demand, now consumed by data center power capacity globally. That crisis is premised on the assumption that computing AI workloads requires the power-hungry GPU architecture that has driven the current data center build-out. Quantum computing challenges that assumption, not by replacing GPU computing, not by making AI data centers obsolete tomorrow, but by establishing, through demonstration in 2025 and 2026, that a category of computations exists that quantum systems can complete at less than 1% of the power consumption of classical equivalents. That category is expanding. And the $400 billion in AI data center capital expenditures that the 5 largest technology companies committed in 2025, the nuclear PPAs, the stranded grid power solutions, the water infrastructure, all of it is premised on the GPU-dominated computing paradigm remaining dominant for long enough to justify those commitments. This video is going to explain exactly what quantum computing has demonstrated in 2025 and 2026, exactly what it cannot do that GPUs can, exactly what the hybrid architecture that is actually emerging looks like, and what it means that the chairman of IBM's quantum program and the corporate vice president of quantum at Microsoft both said in May 2026 that quantum processors will sit alongside GPUs inside data centers, not instead of them. Subscribe right now, because the relationship between quantum computing and the AI data center industry is the most misunderstood dimension of the AI technology transition, and understanding it correctly changes how you evaluate every data center investment, every quantum company announcement, and every claim that either technology is making the other obsolete. The title of this video says, "Quantum just killed the data center industry." The most honest clarification of what that means was provided by Marc Lejour, an IEE member and MBA professor, in a May 2026 article about the quantum and AI data center collision. Think of quantum computers as different types of computers for different use cases. You might have a pickup truck and a small 2-place sports car in your garage. They are both good at what they do. One is not lowering the costs of the other. That analogy is more precise than any simplification either direction. Quantum computers are not replacements for GPU data centers. They are different vehicles for different problems. The workloads where quantum provides an advantage over classical computing are specific, well-defined, and importantly, different from the matrix multiplication operations that make GPUs ideal for training and running large AI models. A GPU training a large language model is an extraordinarily efficient matrix multiplication machine. Quantum computers are bad at matrix multiplication in the way that a sports car is bad at hauling lumber. The computational task that GPUs dominate, processing the attention mechanisms and weight updates of a neural network across billions of parameters simultaneously, is precisely the task for which quantum offers no advantage under current understanding of quantum algorithms. Quantum algorithms provide advantage for problems with specific mathematical structures. Problems where a quantum superposition over many possible solutions allows a quadratic or exponential speedup over the best-known classical algorithm. The canonical examples are Grover's algorithm for unstructured search, Shor's algorithm for factoring large numbers, and quantum simulation of molecular systems. Training a transformer neural network on next token prediction is not in any of these categories. The AI training and inference that is consuming the power in Northern Virginia and Ohio and Dublin and Singapore will continue to require classical GPU computing for the foreseeable future, regardless of any quantum milestone. Subscribe and hit the like button right now, because the workloads where quantum does provide advantage include several that are driving substantial GPU demand right now, and understanding specifically which workloads those are is the part of the quantum data center story that most coverage misses. Drug discovery, material science, financial portfolio optimization, logistics routing, supply chain optimization, weather modeling, and climate simulation are the categories of computation where quantum algorithms provide or will provide meaningful speedups over classical alternatives. These are not niche or academic applications. And they are the specific workloads that Pfizer, BASF, Goldman Sachs, JP Morgan Chase, DHL, and NoAA are paying for compute to run right now on classical hardware. The pharmaceutical industry runs molecular simulation workloads on GPU clusters that estimate the binding affinity of drug candidates to protein targets. These simulations are limited by classical computing's inability to exactly simulate quantum mechanical interactions, which means the simulations use approximations whose errors limit their predictive accuracy. A fault-tolerant quantum computer with enough logical qubits to simulate molecular interactions exactly would provide results that current classical molecular simulation cannot match at any feasible scale of classical compute. Similarly, financial portfolio optimization involves finding the optimal allocation across thousands of assets under thousands of constraints, a problem whose search space grows exponentially with the number of variables, and for which quantum optimization algorithms provide quadratic speedup in certain formulations. Logistics routing across global supply chains involves the same combinatorial explosion. None of these workloads are AI in the neural network sense. All of them are currently running on classical hardware, including GPU clusters, because they are computationally intensive and GPU parallelism helps even when it does not provide the exact speedup that quantum would. When quantum computing achieves fault-tolerant operation at the scale IBM is targeting for 2029 with its Starling system's 200 logical qubits executing 100 million error-corrected operations, a portion of the compute workload currently running on classical hardware will migrate to quantum hardware. That migration is not a replacement of data center infrastructure. It is a change in what hardware data centers need to house. The hybrid architecture that is actually emerging from the announcements of May 2026 is more specific than any of the replacement or coexistence narratives most coverage has provided. Zulfi Alam, Microsoft's corporate vice president of quantum, stated directly in May 2026, "A misconception many folks used to have is that a quantum machine is a standalone entity. It is not. A quantum machine is very much part of the ecosystem. It sits right next to a hyperscaler. Everything else in the rack, the control electronics, the readout systems, the error correction processors, runs at room temperature. A 30 kilowatt rack that fits standard data center space and connects to existing GPU infrastructure through NVIDIA's NVQLink Open Interconnect at 400 gigabits per second, with latency under 4 microseconds, is not the specialized standalone installation requiring dedicated cryogenic facilities that most people imagine when they think of quantum computers and data centers. It is a server rack with unusual cooling requirements for the soda can-sized core. IBM's Jerry Chow, CTO of quantum-centric supercomputing at IBM, stated the same vision from a different angle. We are moving into a data center model where we are actively looking at co-located CPU and GPUs with quantum processors. By the 2030s, Chow said, the industry expects to rethink the supercomputer entirely as a fully integrated system of CPUs, GPUs, and QPUs. The QPU sits alongside the CPU and the GPU. The workload moves between them based on which hardware is best suited to each computational step. The Brownstone research analysis from October 2025 described the exact mechanism. The best utilization of a quantum computing system is to give it the most complex part of the puzzle to solve, the part that is impossible or prohibitively slow for an AI data center to solve in any reasonable time frame, and then have the classical system handle everything else. The hybrid computing architecture that IBM, Microsoft, Google, and NVIDIA are all converging on is not quantum replacing classical. It is quantum and classical specializing and complementing each other in the same facility. The NVIDIA play in quantum deserves specific treatment because it is the most commercially revealing indicator of how the industry actually expects this hybrid future to manifest. NVIDIA is not building quantum processors. It has no qubit program. Instead, it announced NVQLink in October 2025, an open interconnect standard that couples quantum processors from 17 different hardware builders to GPU systems at 400 gigabits per second. It delivers 40 petaflops of AI performance at FP4 precision from the GPU side, while the quantum processor handles the specific computational steps that benefit from quantum speedup. NVIDIA has also integrated Q2AQ, its quantum computing software development kit, with 17 quantum hardware builders and 5 controller builders and 9 US national laboratories. Tom's Hardware noted that while the quantum models running on this architecture are open source, the stack they run on is not. The decoder requires NVQLink's low latency interconnect. The calibration workflows run through Q2Q, and the deployment tooling targets NVIDIA hardware. NVIDIA's bet is exactly the bet it made on AI in 2012. which is that whoever develops the next generation of compute hardware will still need NVIDIA's interconnects, software, and ecosystem to make it work. When quantum processors come into data centers, NVIDIA intends to be the company whose hardware connects them to everything else and whose software tells them what to compute. That is not a quantum bet. It is a GPU bet that happens to include quantum as an accelerator. The business logic reveals the architecture more clearly than any technical description. If quantum were going to replace GPUs, NVIDIA would not be the company positioning itself as the connector between them. NVIDIA is positioning itself as the connector precisely because it does not believe quantum will replace GPUs, but rather because it knows that GPUs alone will not be sufficient for every computation, and that the transition from GPU only to GPU plus QPU creates a new connection problem that NVIDIA can solve. The resource problem that quantum data centers of the future will create is the dimension most relevant to everyone who has followed this channel's coverage of classical AI data center resource constraints. The Science Direct paper published in January 2026 in Renewable and Sustainable Energy Transition, titled Uncertain Quantum Computing Futures and Potential Energy and Physical Resource Impacts at Scale, assessed what happens to electricity, water, and materials demand if quantum computers are integrated into the data center infrastructure at scale between the 2030s and 2045. The paper's conclusion, as TechExplore summarized in May 2026, is that while energy demands may remain within feasible limits, water and material supply could pose significant challenges. The most constrained specific material is helium-3, an isotope used in the dilution refrigerators that cool superconducting quantum computers to near absolute zero. Helium-3 is extremely scarce, primarily produced as a byproduct of the decay of tritium in nuclear weapons, and is already in short supply for the quantum computers being built today at small scale. At the scale of quantum processors being integrated into data centers across the global economy, the demand for helium-3 could significantly exceed available supply under current production methods. This is the quantum version of the gallium and germanium supply chain problem that this channel covered in the semiconductor scripts. A material that nobody thinks about because it is not currently needed at scale, but that becomes a strategic constraint when the technology it enables is deployed at the scale that commercial quantum computing would require. The quantum data center of 2035 faces its own version of every resource constraint that the classical AI data center of 2026 faces: power, cooling, materials, and the infrastructure to supply them. The transition from one computing paradigm to another does not eliminate resource constraints. It changes which resources are constrained. The investment implication of the quantum data center collision, framed by everything this video has covered, is the one that most directly affects the decisions being made in corporate boardrooms and government policy offices right now. The 5 largest technology companies spent more than $400 billion on data center capital expenditures in 2025. The IEA documented that the SMR nuclear pipeline grew from 25 gigawatts to 45 gigawatts in 18 months, driven almost entirely by AI data center electricity demand. Texas is projected to consume 399 billion gallons of water from data centers by 2030. All of these commitments are premised on GPU-dominated AI computing, remaining the primary driver of data center demand for long enough to generate returns on infrastructure that has 20 to 30-year useful lives. The quantum data center hybrid architecture that IBM, Microsoft, Google, and NVIDIA are all describing as the 2030s target does not invalidate those returns. It redirects a portion of new data center investment from pure GPU clusters toward quantum GPU hybrid facilities, which have different but not necessarily lower infrastructure requirements. The 30 kilowatt Microsoft quantum rack that fits a standard server space does not add to data center power demand the way a Blackwell NVL72 rack at 130 kilowatts does. But it adds to the facility's complexity, its cooling requirements for the cryogenic core, its materials supply chain, and its maintenance requirements. The data center industry does not get killed by quantum computing. It gets more complicated by it. Subscribe to this channel. Because the data center industry's evolution from GPU only to GPU and QPU hybrid, and the specific infrastructure, resource, and supply chain implications of that evolution will be visible in real capital commitments and real facility designs over the next 5 years. And this channel will cover each development as it becomes visible. The specific timeline question, when quantum processors actually arrive in commercial data centers at meaningful scale, has been answered by the most authoritative voices in the industry with enough specificity to allow serious planning. Google CEO Sundar Pichai said in late 2025 that the company is optimistic that practical quantum workloads will emerge within 5 years, meaning by approximately 2030. IBM set 2026 as a crucial year to demonstrate quantum advantage on specific scientific workloads under its quantum-centric supercomputing architecture, and its Starling fault-tolerant system targets 2029 with 200 logical qubits and 100 million error-corrected operations. Microsoft's Majorana 2, announced in June 2026, represents the topological qubit approach to achieving the hardware-level error correction that reduces the overhead, that makes fault-tolerant quantum computing impractical in current superconducting architectures. DARPA's quantum benchmarking initiative selected Microsoft and PsiQuantum for its final validation phase, targeting utility-scale quantum by approximately 2030. The convergence of these timelines places the first commercial quantum computing deployments in data center environments in the 2029-2031 window, with scaled deployment across the 2030s. The quantum computing claims that Jensen Huang mocked in early 2025 as being 20 years away were already becoming less accurate by the end of the year. The Quartz headline from May 14, 2026 captures the current consensus. AI data centers and quantum computing are about to collide, not have collided. About to. The collision is in progress and the industry is designing for it, but the commercial scale collision is approximately 4 to 6 years away from meaningful data center deployment. Quantum just killed the data center industry is a title that describes a momentum shift, not a completed event. The death notice is premature. The obituary is being drafted. Subscribe to this channel. Like this video, because quantum computing is arriving in data centers as an addition, not a replacement, and understanding the specific workloads, the specific hardware, the specific resource constraints, and the specific timeline of that arrival is the analytical capability that separates informed decisions about AI infrastructure, enterprise computing, and technology investment from the noise of every headline that either dismisses quantum as decades away or declares it an immediate replacement for everything classical computing does. Quantum just changed the trajectory of the data center industry. Whether it has killed it depends on what you think the data center industry is for. If it is for running GPUs, it is fine. If it is for providing the best available computing for every problem humanity needs to solve, it is in the middle of the most significant architectural transition, since the GPU replaced the CPU for parallel workloads. The transition is measured in years, not quarters. The consequences are measured in the investment, the infrastructure, and the resource supply chains of the decade ahead. This channel will follow every milestone in that transition as it becomes visible. Stay with us. The specific workloads that quantum computing will execute in data centers by 2030, pulling computational demand away from GPU clusters, deserve naming precisely because they determine which industries' AI data center investments are most exposed to the quantum transition and which are least exposed. Drug discovery is the highest confidence near-term quantum workload. The pharmaceutical industry's use of molecular simulation to identify drug candidates is limited by the classical approximation of quantum mechanical interactions, and the economic value of improving molecular simulation accuracy is enormous. Each failed drug candidate that classical simulation inadequately screened costs hundreds of millions of dollars to discover in clinical trials. IBM's partnerships with major pharmaceutical companies for quantum drug discovery access are premised on this value proposition, and IBM's quantum researchers have demonstrated quantum advantage on small molecular simulation problems that validates the approach's potential at larger qubit counts. Materials science is the second high-confidence workload. Designing materials with specific electrical, thermal, or structural properties. For applications from battery anodes to photovoltaics, to semiconductor substrates requires simulating quantum mechanical interactions at the atomic level, and better simulation leads directly to better materials. Cybersecurity is the third major workload, specifically the cryptographic workloads involved in breaking encryption using Shor's algorithm, which this channel has covered extensively in the quantum encryption scripts, but also the post-quantum cryptography, testing, and verification workloads that defend against that threat. Financial optimization, logistics, and climate modeling are medium confidence workloads where quantum speedup has been demonstrated theoretically and in small-scale experiments, but where the specific economic advantage of quantum over best-in-class classical approaches for real-world problem sizes remains an active research question. AI training and inference, the workloads that currently account for the largest share of GPU data center power consumption, are low-confidence quantum workloads. The specific mathematical structure of neural network training does not straightforwardly admit quantum speedup under any currently understood quantum algorithm. This distribution of workloads confirms the pickup truck and sports car analogy. The workloads that quantum will displace from classical hardware by 2030 to 2035 are not the workloads currently driving the largest data center capital expenditures. The GPU data center build-out is primarily justified by AI training and inference demand. Quantum computing primarily addresses a different set of scientific and optimization workloads. The two computing paradigms will coexist in the same facilities, connected by NVIDIA's NVQLink and IBM's hybrid architectures for the foreseeable future. Subscribe. The workload analysis is the foundation of the entire quantum data center investment thesis, and this channel will track the progress of each workload category as quantum hardware scales toward the parameter regimes where advantage over classical alternatives becomes commercially meaningful. There is one more dimension of the quantum data center collision that this script has not yet addressed, and that the title most provocatively invokes. The data center industry as it currently exists is organized around a specific technology stack. NVIDIA GPUs for compute, Blackwell and Vera Rubin for AI, liquid cooling for heat management, direct current power distribution, and fiber and NVLink for interconnect. Every data center being built in 2026 is optimized for this stack. The data center industry that will exist in 2035 is organized around a different and more complex stack. The same GPUs for AI training and inference, plus QPUs for molecular simulation and optimization, with dilution refrigerators or the room temperature quantum alternatives that research like the Stanford December 2025 paper is pursuing, connected through NVQLink type interconnects at low latency, running QDay-Q or equivalent hybrid programming environments. The firms that build data centers today, the Equinixes, the Digital Realties, the Cyrus Ones, and the hyperscaler facilities of Amazon, Google, Microsoft, and Meta, are designing facilities in 2026 that will need to accommodate hardware they have not yet specified, meeting power and cooling requirements they have not yet fully modeled, for workloads they have not yet benchmarked at commercial scale. This is the sense in which quantum just killed the data center industry as it exists. It has not made current data centers obsolete. It has made the design assumptions underlying current data center construction inadequate for the data center of 2035. The capital commitments being made now for 20 to 30-year facilities are being made on specifications that the quantum transition will require to be revised. Whether that revision happens before or after the concrete is poured is the specific question that will determine how much of the $400 billion currently being deployed in data center capital ends up in facilities that need to be significantly retrofitted to accommodate the quantum GPU hybrid architecture that is already visible on the horizon. Subscribe to this channel. The data center industry is not dead. Its current form has a shorter useful life than the facilities being built this year are designed for. That is the version of quantum just killed the data center industry that is accurate. The three most important numbers to carry away from this video, numbers that translate the quantum data center story into the specific analytical framework most useful for evaluating future announcements: 7 kilowatts, 30 kilowatts, and 132 kilowatts. QuEra's 256-qubit quantum computer at 7 kilowatts can solve certain problems that no classical computer can solve in any feasible time. Microsoft's Majorana quantum rack at 30 kilowatts, fitted in a standard server space, will coexist with GPU clusters and hybrid data centers beginning around 2030. And NVIDIA's GB200 NVL72 at 132 kilowatts will continue to dominate the AI training and inference workloads that are driving the current data center build-out, regardless of what quantum achieves. When a company announces a quantum computing milestone, the most important question is not whether the quantum computer is powerful. The right question is which workload it is accelerating, and whether that workload is currently running on GPU clusters that it would partially displace, or whether it is a new workload class that quantum uniquely enables and that classical hardware cannot serve. When a data center company announces a new facility, the right question is whether its design accommodates the 30 kilowatt quantum rack that IBM and Microsoft say will be in data centers by the early 2030s, or whether it is optimized exclusively for the GPU architecture that will share that future data center with quantum processors. The quantum data center collision is real, documented by the largest players in both industries, and on a timeline that is close enough to affect current capital allocation decisions. Quantum just changed the data center industry's trajectory. The title said, killed. The reality is changed. But changed is the more interesting story. Subscribe. Stay with this channel. The next chapter is being written in the data center design decisions of 2026 and in the quantum hardware milestones of 2027 through 2030. This channel will follow every chapter.